Hello everyone, in this video we're going to go over section 4.3 on direct proof and counterexamples. Now let's talk about rational numbers. So a real number R is says to be a rational number if and only if it can be expressed as a quotient of two integers with a non-zero denominator. Or we can also say that a real number that is not rational will be irrational. Symbolically, what this is going to mean is that if R is a real number, then we have integers A and B, so that R can be A divided by B, and we're assuming that B is going to be different from 0. In our instances, you can also talk about B being just the natural numbers, since you can just keep A being a negative number and cover all negative numbers. So you can also get the definition of A being an integer and B being a natural. That will cover also the fact that B cannot be 0. Now, notice that the fraction does not need to be in the lowest term, the lowest common denominators, or the simplified version. You can have multiple rationals that are not simplified, and all integers are going to be rational by definition. We're going to have with B equals 1. Now, some examples of rational numbers are going to be fractions like 3 over 4, minus 2 over 5, which are the natural expression of rational numbers. But you can also have rational numbers that come from decimals. Like, for example, 0.75. 0.75 also come from the fraction 75 over 100, which, if you simplify that, it will be the same number that 3 over 4. This is what we call a rational with a terminating decimal number. We have all the integers, of course. So, for example, 2 can be seen as 2 over 1, minus 7 over 1, so on and so forth. 0 is 0 over 1. But we also have decimals that have repeating patterns. So, for example, 0.33333, and then there is an infinite amount of repetition of the same pattern. This is going to be equivalent here to the 1 over 3, and is the representation of a rational with repeated decimals. Now, some irrational numbers and oppositions are going to be numbers like square root of 2, square root of 3, square root of 5, pi, the Euler number, the golden ratio. All of those are going to have their decimal form as well, but what you're going to find out about the irrationals is that they don't have a pattern, and they're infinite as well. So let's see a couple of rationals here. We minus 4 over 5. Yes, this is going to be irrational. We have minus 4 and 5 are both integers. 5 is different from 0. So it holds the definition. The minus 4 over 5 is rational. 5 or minus 5 could be irrational. You can see 5 as 5 over 1. And 1 is different from 0. So they're both integers. So by definition, we'll hold that 5 is irrational. Now, 3 over 0 is irrational. The answer is no. This is undefined. We cannot divide by 0. So 3 over 0 is not going to be a number at all. So we cannot classify it either as a rational or irrational. Now, all terminating decimals are rational. All repeated decimals are rational, but non-terminating and non-repeating decimals are going to be irrational. So let's give one example of how you find this. And how do you find the fractions that are equivalent to this? So consider the repeating rational or the repeating decimal 0.45, 645, 645, 645. You can see this as 0.456 periodic. And so the way that we do this to represent in fraction is we look for a way of removing at least one of the parts that is decimals and put it at front as a rational. So, for example, the pattern here is that 456 is repeating. So I'm going to multiply by 1,000 so I can get at least a 456 at the front, and then I get a 0.456, and then 456 keeps repeating. But the idea of doing that is so I can make a subtraction. So, for example, here, if x is this and 1,000 of x is this, then I can do a subtraction between 1,000 x and minus x, and that's just going to give me the 456. So it's going to give me the integer part of this subtraction. And now Notice that this difference here is going to be 999. So this tells me that I can simplify and I can represent x as 456 over 999. I can simplify that to 152 over 233 by divided by 3 up and down. But since we just represented this number as a quotient of integers with non-zero denominator, then it's going to be a rational. And this is one of the ways that we can transform decimal repeating numbers to rationals. Now let's talk about some properties. One of the most important properties of the real number is going to be the zero product property. That is that if you have two numbers that are not zero, then the product is not going to be zero. So for example, using quantifiers, that will mean that for all a and b that belongs to the real numbers, if a is not zero and b is not zero, then a times b is not going to be zero. The contrapositive of this is that for all b that belongs to the real numbers, if a times b is equal 0, then either a is equal 0 or b is equal 0. So this means that if the product of two numbers is 0, it's because one of them gotta be 0. Now, why this matters? We use this property to solve equations constantly. So for example, if we have an equation of the form x minus 2 times x plus 3 equals 0, then that tells me, hey, x minus 2 gotta be 0 or x plus 3 gotta be 0. And that's going to help me solve the equation. Now, let's build some theorems about rational numbers. Now, let's prove that every integer is a rational number. So consider any integer. So let n be an integer. The show is to show that it's a rational number. Well, what do we need to show really? We need to show that it says numbers a and b so that n can be represented as a over b. And b is going to be different from 0. In particular, we can just pick a, b, n, and b, b, 1. And so this will work. As verification, a equals n is an integer, that's given. B equals 1 is an integer. B is different from 0. And I can represent a over b equals n over 1, and that's going to be equals to n. So that will give me the by conclusion, by definition of the conclusion, n is going to be rational. Since n was an arbitrary number, every integer is going to be a rational. Now let's prove that the sum of any two rational numbers is rational. So first, the assumption is, let's say R and S are rational numbers, and then the definition of this means that R can be represented as A over B, where B is different from 0, and A and B are integers. And similarly, S can be seen as C over D, where C over D are integers, and D is different from 0. So now, because of this, we go to the third step, our manipulation. We're going to add R and S, and that's going to give me A over B plus C over D. We multiply the A over B fraction by D, and we multiply the C over D fraction by B, so we can have common denominator. And now we can join that in a single fraction. It's just going to be A times D plus B times C over B times D. Now, this common fraction is going to have a top that is an integer, since multiplication and sum of integers is going to be integers, and multiplication of integers is integers as well. So the top and the bottom are both integers, and because both B and D are not 0, then B times D is not 0. Hence, if I call P AD plus BC and I call Q B times D, we're gonna have that P over Q is a rational number. It holds all the different things and conditions that we need to make it an integer. And so we're gonna get that R plus S is a rational this way. Notice that we're going over the 5 step. We go the assumption, then the definition of the assumption, the manipulation, the definition of the conclusion, and we finally reach to the conclusion. This is approved by the 5 steps, is the ideal way to prove things. Now, this theorem is saying that the rational numbers are close under the addition. So pretty much if you pick two rational numbers and you add them, you're going to get a rational as well. This is called close. That's not something that happens for every set. For example, irrationals are not closed. The sum of two irrationals is not necessarily going to be irrational. We'll see that later. Now, the natural transition from that theorem is now we proved that the sum was rational. So, what about the product? And indeed, the product of any two rational numbers is also going to be irrational. The way that we go about it is the same. We assume that we have two rational numbers in the assumption. R and S are rational numbers. So, step number 2, definition of the assumption. Is going to be integers a, b, c, and d, so that R can be represented as a over b, and S can be represented as c over d, and b and d are different from 0. So our manipulation is just going to be multiply, and when we multiply, we get that R times S is just going to be a fraction of the form a times c over b times d, and a times c is going to be my p, b times d is going to be my q. They're going to be integers because they're multiplication of integers. And they're non-zero since each of them is non-zero by the set of property product. We're going to have that as non-zero. And so by conclusion, the product of the two rational numbers is going to be rational as well. Now let's talk more about closure properties. The rational numbers will be closed by what we just proved, by addition, by subtraction, by multiplication, and by division. In particular, addition and subtractions are the same thing, and division and multiplications are the same thing. We're just using multiplication by the opposite, additive positive here, the additive opposite, and then here we're using for division, we're just multiplying by the inverse. So essentially, those properties apply, and we have that is the rationals are closed under all the operations. Now, it's important to check that irrationals are not closed under different things. So, for example, square root of 2 is irrational, although 2 belongs to the rational. So, if we do a root, then it might not be a rational anymore. Root 2 is actually going to be an irrational number. So now let's talk about common mistakes that we can do when dealing with rationals. You might think that all decimals are terminating. You got to be very careful when you're using your calculator because sometimes your calculator is just going to give you a fixed amount of decimals, and none all the decimals are represented. So you got to be careful about understanding if the number that you're showcasing indeed is a rational or irrational. A square root of 2 can be seen in a basic way as 1.414, and so some people cut it there and think it's irrational, but it's not. There's a bunch of different non-terminating, non-repeating numbers that continue, so square root of 2 is going to be an irrational. It's very important that you verify all the integers requirements when you're proving sum and product is rational. You need to verify that numerator and denominator are integers. And things like since A and C are integers, then the product is an integer as well. You also need to not forget to verify the denominator is non-zero, because if you're dividing by 0, then everything is wrong. So you got to be careful with that. Now 0 over 0 is also undefined, is not 0. The only way that you get to work 0 in irrational is when you represent 0 over any other number. So for example, 0 over A is going to be 0 when A is different from 0. But in general, any number over 0 is always going to be undefined. Now, not all square roots are irrationals. The square root of 2, square root of 3, square root of 5 are irrational, but things like a square root of 4, a square root of 16, a square root of 64 are perfect square, and they're going to be rational numbers. So you got to be careful with the roots too. Not all the roots will be irrationals. The decimal notation is not enough to show that it's proof. So, for example, saying that 1/3 is irrational because 0.333 goes on forever is a bad reason to think that it's irrational. You got to remember that if we have a repeating pattern, then it's likely that you can represent that as a fraction. And one of the things that we're going to see on the exercises from this section is how to convert more repeating decimals to fractions. So in summary, the key concepts here are the rational numbers that you can represent from the form a over b, with a over and b being integers and b being different from 0. All integers are rational, and terminating and repeating decimals are rational. We have the zero product property. If we have two numbers that are not 0, the product is not going to be 0. And the contrapositive, if you have the product of two numbers being 0, then one of them got to be 0. And the rational numbers are going to be closed under sum, subtraction, multiplication, and division. However, it's not closed under roots. All right, let's see more of this on the class notes exercises.